Hello, I am Jan Solanti from the Customized Parallel Computing Group at Tampere University. I'm presenting PoCL-Remote, a distributed OpenCL runtime with a focus on low latency. Traditionally, the focus of high-performance computing has been with supercomputer clusters and scientific applications where scalability is extremely important, but latency is not a high priority. Similarly, complex compute tasks can be increasingly found in user-facing real-time applications where latency is often a key metric. PoCL-Remote provides an implementation of the standard OpenCL API meant for high-performance computing. It achieves throughput scaling by offloading compute tasks to one or more compute nodes on a network, while still maintaining low latencies necessary for real-time applications. Application development has strongly shifted towards mobile devices as the main target platform. However, mobile devices are way behind desktop hardware when it comes to performance and additionally limited by their battery life. As such, many tasks are simply not feasible to run on a mobile device. The easy solution is to offload heavy workloads to a dedicated compute server, but as many applications require real-time results, network latency often limits the viability of such a solution. This is especially problematic on wireless connections that mobile devices rely on heavily. The latest generation of wireless communication standards, 5G and Wi-Fi 6, have reduction of the first hop latency as an explicit goal, making offloading computations to a private cluster or cloud edge server near the base station an interesting solution. In this context, PoCL-Remote was created as an OpenCL runtime that could make use of GPUs as well as custom accelerators over a network. PoCL-Remote appears to OpenCL applications as just another OpenCL driver and requires no changes to the application source code for its basic functionality. Internally, it delegates API calls to a daemon running on the remote server. The daemon then executes these calls on an OpenCL driver that is available on the server, which can be a vendor-provided driver, a CPU or FPGA-backed portable CL instance, or any other conformant OpenCL implementation. PoCL-Remote is not the first implementation of such a runtime, but prior solutions have been mainly concerned with throughput and seeing whether or not offloading OpenCL tasks is feasible at all. PoCL-Remote, on the other hand, has an explicit focus on minimizing latency. Most networked applications rely on generic network protocols that have some kind of custom data format for the data being transferred over the wire. This adds a serialization and deserialization step on the ends of the communication channel, which has proven to have significant performance impact. One of the methods used to achieve low latency in PoCL-Remote is the custom network protocol that unifies the in-memory and wire representations of OpenCL commands and data to eliminate serialization and deserialization steps. Most PoCL-Remote use cases assume the host application to run on a mobile device with modern wireless connectivity, that is to say 5G and Wi-Fi 6. Being radio-based connections, they are sensitive to other traffic and noise on the same and nearby frequencies, which contributes to packet loss. Practical latencies are still in the order of several milliseconds. In existing solutions, node-to-node data transfers generally go through the host application, which means they incur the limitations of the wireless connection twice. Remote nodes are assumed to be stationed in a private cloud or cloud edge cluster, meaning the remote nodes have wired, generally data center-grade connections to each other. This implies massively higher available bandwidth and lower latencies all the way to sub-microsecond numbers. For minimal latency to the mobile device, remote nodes are to be placed physically close to the wireless access point. In addition to nodes having great connectivity to each other, a single node can contain multiple compute accelerators. Communication between accelerators on the same node does not need to touch the network at all and thus has excellent latency and throughput characteristic in comparison. PoCL-Remote supports both node-to-node and accelerator-to-accelerator transfers and automatically chooses the fastest available transfer type. Applications can request OpenCL commands to be scheduled in submission order or based on completion events they emit. One use of the peer-to-peer connections between remotes is to allow them to notify each other of command completion, letting others immediately begin executing commands that are now unblocked. Here, the solid green arrow illustrates a simple OpenCL command from the application. The command is sent to its target remote, which executes it and sends a completion notification indicated by green dotted arrows independently back to the application and to all other remotes that may be waiting for the completion of this command, eliminating the need to wait until the client application has received the notification and dispatched new commands. The effects become even more noticeable when offloading commands that require moving large data buffers between remotes, as illustrated with the solid red arrows. In such cases, the application would send the command to the remote that has the most up-to-date version of the buffers. This remote then sends the buffer and the command directly to the target remote. The target remote then completes the command and notifies the client and the other remotes as usual, depicted with the dashed red arrows. Peer-to-peer connections between remote nodes also allow efficient communication with more specialized devices, such as networked cameras. For example, an application that requires a video feed and some heavy pre-processing can stream video directly to a powerful compute node and the handheld client device. The compute node can do the heavy pre-processing and send its results to the client device, reducing the end-to-end latency and power consumption on the client device. Latency introduced by the PoCL-Remote framework was measured with a set of synthetic benchmarks. This diagram shows the latency from enqueuing a compute kernel that increments a single integer and reading the result back to the host application. The measurement was conducted using a local GPU and its vendor-provided OpenCL driver, PoCL-Remote, as well as the SNU-CL cluster runtime that is considered the current state of the art. Scalability across an increasing number of remote nodes and GPUs was measured with a distributed matrix multiplication benchmark, yielding similar results to the state-of-the-art implementations. For a benchmark resembling real-world use, a case study was conducted using an application that displays animated point clouds in augmented reality. In order to improve the quality of the rendered point cloud, the points are sorted back to front and their edges are smoothed using alpha blending. The sorting is done on the remote and the results are written to an index buffer that is then transferred to the host application for rendering. Rectangular artifacts can be easily seen on the naive rendering displayed on the left. Sorting and smoothing the points eliminates these as seen on the right. When offloading the sorting of the points to a more powerful remote GPU, we observe great wins in frame rate and a massive decrease in energy consumption. On the left is a demonstration of the application doing AR tracking, point sorting, and rendering all locally on the system on chip. On the right, the sorting phase is offloaded to a more powerful GPU across a Wi-Fi 6 network. The frame rate improvements are summarized here. Offloading the sorting of points naively yields only a meager improvement. If the application is made more aware of the remote driver's capabilities, however, frame rates can be improved easily by a factor of 10. Looking at the energy consumption of the application paints a very different picture. Enabling AR tracking in addition to sorting the points on the system on chip turns out to consume a huge amount of energy, but offloading the demanding point sorting phase offsets this increase almost entirely. With additional optimizations, it is possible to bring the total energy consumption down below that of the baseline of fully local rendering without AR tracking, essentially making it possible to both add AR tracking to the application and simultaneously improve battery life of the handheld device. PoCL-Remote is implemented as a client library to be linked to the host application running on the mobile device and can coexist with native OpenCL implementations. Planned improvements for the future include on-the-fly detection of available remotes and roaming between remotes as network conditions change. We are also looking to extend the support to Vulkan compute shaders for uses such as distributed path tracing in virtual reality applications and are interested in hearing about more benchmarks and application scenarios.